So for this lesson, I just kind of want to go over some application problems that we haven't gotten to in some of the other sections. All right. And you'll see some of these application problems probably on your lab. You might even see one on the test. So I kind of saved them to the end to go over them. I'll tell you, they're just from section. So the first one is 2.5 from section 2.5. So again, these are just some limit application problems. From 2.5 and 2.6 mostly. Please note, we as a class did not go over 2.7. 2.7 is the detailed definition of a limit. So what does that mean? I don't know if you recall back when we did limits, I said, you know, as we get arbitrarily close to a number, the detailed definition of a limit actually defines how you determine how close it is. So if you're a math major, I would suggest maybe reading over 2.7 and seeing if you can understand that formal definition of a limit. If you're not a math major, just ignore it. We're ignoring it. How's that? So you business majors, engineering, physics, computer science, you don't necessarily. But if you happen to be a math major, you know, if you were taking an honors course in calculus, we'd spend time on that, all right? So let's talk about an application. So let's suppose we have a colony of squirrels, like actual squirrels, all right? So you may recall things like population growth and stuff like that can actually be represented by functions. So this growth of this colony of squirrels, it was either that or bacteria. I thought squirrels would be way more interesting to talk about. So growth of a colony of squirrels can be represented by the function population at a given time, all right? So when we set functions up, we kind of like to use a letter that represents what we're talking about. That's where the P comes from, it's population. And then our independent, P is the dependent variable, dependent upon time. The independent variable is T, so we're going to use time for this one. So this particular squirrel colony grows at this rate. So it's 1,500 divided by 3 plus 2e to the negative 0.1 t. So yes, this is something that mathematicians actually do. They take things like growth. Sometimes it's bacterial growth, really important when dealing with such things as a pandemic, and growth of a population, and they examine it and build a function for it, all right? So then you know, oh, in 10 days, how many squirrels will I have? All right? You can actually determine things like at the very beginning, time 0, how many squirrels do I have? Right? So you can determine various things here. And how would you determine time 0? You would go ahead and plug in 0 for t, right? So what does that mean? So initial at time 0, well, to grow squirrels, I need to start with squirrels, right? You can't start with no squirrels. So we got to have some squirrels. So how many squirrels do we have in the beginning? Oh, well, that would be P of 0 over 2e 0.1 times 0. All right, so you're going to need your calculators for this one. So let's calculate this. It will be 1,500 divided by, okay, what's e to the 0, everybody? 1, right? E to the 0, 1. We go with that? So it's 1,500 divided by 5. We didn't need a calculator for that, did we? I'm sitting like, oh, we're going to need a calculator. Yeah, we did not need a calculator for that. 300. All right. So again, you can't study a population of squirrels without starting with a few squirrels. So we're starting with 300 squirrels. And you get the idea. You can determine, so this particular time, it doesn't tell you. Does it tell me in the problem? Doesn't tell you what kind of time we're talking about. You can assume years, I guess. I don't know. Whatever the time is. So you can say after 1 year, after 2 years, how many squirrels will I have? So here's the question. Squirrels continue to populate, correct? Do they populate, and does this number go to infinity? What do you think? Population represents the number of squirrels I can count at any given time. Will that number go to infinity? Give me some arguments. No, why not? Okay, there's probably not enough food. And what happens when we all get older? We die. Squirrels die. So do you understand? It doesn't grow infinitely, correct? The question becomes, though, does the death rate become more than the birth rate? So think about that for a second. If the birth rate is quicker than the death rate, could it grow infinitely? Yeah, right? So these are the important questions to ask. The good news is we can figure that out mathematically because a function was built. Okay? So here's the question. Does the population here reach an equilibrium? You know what I mean by that? Does it reach a number where death balances birth and it never goes above that number? There's another name for that. It's called steady state. So the question you're going to be asked is, will this population reach a steady state? So steady state means as time goes on into infinity, which we would love to think happens, right? If not, the whole world is blown up. As time goes into infinity, does the population reach a steady state? What are we looking for mathematically in this problem? What are we looking for mathematically? If I were to graph it, what could you draw to represent this? There's a word for it. We spent a whole section on it last class. A horizontal asymptote, right? Because that's what happens. When you take your independent variable, in this case it's t, to infinity, what are we looking for? We're looking for the limit as t goes to infinity, which means we're trying to determine, does this function have a horizontal asymptote? Okay? So do you see a connection to an application problem? That's what I'm trying to show you. It works with bacterial growth, decay, and all sorts of things like that. All right? So what are we looking for? When you get a problem like this, and you're given some crazy function, it might ask you things like, hey, what's the initial population? We just did that. It might ask you, what's the population after 5 years? You can plug in 5. Now it's going to say, will the population reach a steady state? That's going to click in your head to do a limit. I want the limit as t goes to infinity. I only care about positive infinity because time, we're not going backwards in time, we're only going forwards. So we're going to use some things that we learned last class to determine that. Number one rule of limits, you always try doing what? Just plugging it in. even infinity, we can try it, right? Because we learned some things about infinity that could allow us to plug it in. This is not the type of rational equation we're used to. This has an e in it, so this is good. This is also a nice little review of an e value, okay? So let's do it. Let's just go ahead and see what happens. Well, oh, I don't need to write. So another key. Notice I'm plugging in infinity. I don't need to write the word limit. If I was simplifying the expression, I would need to keep limit in there. So, oh, well, it's 1,500 over 3. All this is good so far. I don't need to do anything with that. Okay, I'm taking t, which is infinity, and I'm multiplying it. I don't care what that number is. I don't care if it's negative 1,000 or negative 1/10. What am I multiplying it by? That's important there. A negative. Everybody see that? So what's infinity times any negative number? Yeah, it's negative infinity. All right, so now I'm going to just take this little piece for a second. What is e to the negative infinity? So let's think about that. All right, well, anything to a negative power is a reciprocal, right? You flip it. So isn't e... So here's the cool thing about limits. Yeah, we learn a lot of rules. Then you get the problem that doesn't go into any of those rules, and you just have to think through it critically. So e to the negative infinity, you go, all right, I got a negative exponent. Maybe I can figure this out that way. Okay? So now, if I take a number e, which is, okay, e is just a number. We did it in the lab. It's like 2.718, blah, 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 blah. I'm raising it to infinity. What do I get? I get infinity. So, okay, this is the same as saying, what did we learn that 1 over infinity, it doesn't equal, but what did we learn about 1 over? If you take 1 over a number and you keep increasing that number, what does that go to? 0. So in your world, in this world of limits, 1 over infinity becomes 0. Good? Oh, 0. I'm going to take that. So I just kind of did that off to the side, and I'm going to put it back in my problem. There we go. All of a sudden, a problem that looked kind of hard because it had an e in it wasn't that hard. Because now, I can even do this one without a calculator. It's 2 times 0 is 0. What's 1,500 divided by 3? You start with 300 squirrels because of death and birth and lack of food and all this other stuff that's happening. You'll never get past 500 squirrels. That's your steady state. Okay? So when we talk about steady state, where do limits apply? Here's a great application of a limit. I want to play with this in Desmos for 1 second. I have to leave the screen. All right, everybody good? I'm going to leave the screen. I'll get back to it. Let me pop over to Desmos. Everybody has this written down in case by the time I get there, I forget it. When plugging something in Desmos, it's not that hard. Just be careful with the graphs. So, you know, normally your Desmos, I don't know. Again, I told you with Desmos, I'm trying to get it back to like what your Desmos would likely look like. I was playing with this earlier. There we go. Thank you. I was trying to get it. I don't even know every feature of Desmos. All right, let's plug it in. 1,500 divided by, not too bad. So what is it? It's 3, right? Plus 2. You know what's nice about E? You can look for it under functions, or Desmos will actually just take the letter E and it'll know what that means. Okay? It knows it's a function. See, it's already started to calculate it for you. We don't want that. Raised to the negative 0.1. So instead of using t we can make this easy and just use x. I think you can change the variable in Desmos. I'm just not sure. You have to do something else. If you just plug in a t, you're going to get an error. All right, but you can somewhere, you can just use x, honestly, when you're using Desmos. It's just quicker. All right. To use t, you have to, does anybody know, you have to change like the variable somewhere? I can't remember. Just use x. When putting in Desmos, just use x. Doesn't matter what the original problem was. So that's going to be your first mistake if you don't do that. Notice. Okay. I got nothing because of my window. We were working with some bigger numbers. Again, this is why I like touch screens. But if not, you have to go into the wrench and you got to start moving that window around. Okay, think about those numbers we got. We got things like 300 and 500, so you've got to start to play with that window. I'm just going to bring it down until I find my function. There it is. All right, does this function make sense for what I did? Yeah, guess what? And you can put your finger on it. Yeah. There's your steady state. Okay. So, you know, any steady, they're not always. If we put in a function that went to infinity, then you wouldn't have a steady state. You would say, no, there's no steady state. The population will grow infinitely. Okay. I think there's some cool, I don't know how cool it really is since we just lived through a pandemic, but there's some problems we do later in the course that look at whether a pandemic will literally wipe out the population or population survives and pandemic gets wiped out. So that's an interesting one. We survived this one, so we're good. All right. We did anyway. Not everybody did, unfortunately. So that's your steady state. Are we good? I should stop talking. I'm going to get myself in trouble. I like the steady state problems. I kind of like once in a while taking what we do. I mean, this course is very big on just working out problems, but it's nice to get an application in there and see where we can use it. So that was your limits at infinity application from 2.5. At the end of 2.6, we have another application that we're going to look at. And this revolves around what we call, this is from 2.6, the intermediate value theorem. I'll show it to you on a graph first, and then I'll write out the theorem in words for you. It's kind of a little bit of a common sense theorem. Like you're going to look at it and be like, well, that makes sense. Hopefully you'll look at it and think that way. So let's suppose, I'll show you, we'll do a little picture first. All right, so we got some function from A to B. We're just going to look at the function from A to B. I don't care about anywhere else. So I'm going to start it at A, and I'm going to go up to B. All right, so there is our function. This is f of x. Now, the intermediate value theorem kind of states that as long as your function is continuous, and we already learned what continuous means, right? As long as your function is continuous, there has to exist some number, C, that is between A and B, all right? Such that f of C equals L this would be f of A, right? And then that would be, and L is literally between f of A and f of B. In other words, let's get rid of the F's of A's and B's and C's for a second. There's some value X between the endpoints of that continuous function where there's a Y value that's between the Y value of those continuous functions. It's kind of common sense. It says there has to exist that value where F of C has a value in between F of A and F of B. So what does this look like in terms? Again, suppose, we start with suppose. This only works if it's continuous. F is continuous. On the interval. A to B. And L is a number between F of A and F of B. Then there must exist at least one number C in the interval AB such that F of C equals L. We're going to do an application of this so it makes more sense. The reason there's a difference in the brackets that I use. So when we talk about continuity between and in an interval, we have to include the endpoints. Okay. For a function to be continuous from A to B, it also has to exist on A and B itself. So that's why here we're talking about continuity. We're including A and B. When I get to this part, this number C cannot be equal to A or B. Can't be an endpoint. Does that make sense? Mm-hmm. So for this one, again, let's do an application problem because I think it'll make, like, you're looking at it, you're like, yeah, of course. Now, the thing is, a couple things can exist here. Number one, you can have more than one. That's why it says at least one number C. Because if my function kind of looked like, I'll show you. Here's my A and B again. Everybody see that? What if my function looked like that? That's still a continuous function between A and B. You agree? All right. There's A, B, F of A, F of B. There's my L. How many value C's are you going to be able to find? Yeah. So it says at least one. There could be more than one. The other thing is the idea of continuity. Would this work if it wasn't continuous? There's L. Are you going to be able to find a value? No. So it has to be continuous for this to work. All right. So let's do a quick application problem on this one, and then we'll be done with today's lesson. All right. So we're going to do an interest rate problem here. So here's an application. Let's suppose you invest $1,000 in a 5-year savings account. So we're going to invest $1,000 in a 5-year account. Your function, the amount of money A let's call the interest rate R. So that's going to be our variable because the amount of money you're going to have is going to be dependent upon that interest rate. All right, time is fixed, do you notice? Time is just 5-year account. But the amount of money you have is going to be dependent. So the amount of money A is going to vary depending on what the rate is in this particular problem. I know, there's something flying around. All right, and it's going to look like this. You might remember these from pre-calc. You did some interest problems in pre-calculus. I think the 12 comes from there's 60 months. That's where the 60 comes from, 12 months a year, that kind of thing. Okay, so that's what your account looks like. So now, all right, it's a little silly because you're going to go with, you're always going to pick the highest interest rate, but you don't always pick the highest interest rate because some investments come with risks. So there might be reasons why you might not pick the highest interest rate because you're going to sit here, well, why wouldn't I just go with the highest interest rate? All right. But again, some investments do come with risks. So you have some issue there. So your goal is to have $1,400 after 5 years. I'll also tell you there's probably an easier way to make $400. Just saying. I'm just trying to get the information without writing everything down. So what we're going to do is use the intermediate value theorem to show there is a value. IVT is intermediate value theorem. There is a value R in the interval 0 and 0.08. That is an interest rate between 0% and 8% for which A sub R equals 1,400. So use the intermediate value theorem to show there is a value R in 0 to 8. That makes A sub R equal 1,400. So in order to do this, all you have to really do is think about the graph we did and say, all right, all I need to show is that 1,400 falls somewhere between A sub 0 So I just need to find a bank somewhere in there. And how would you do that? All you got to do is plug in the endpoints. You got to find those f of a's. You've got A. A is 0. B is 0.08. Okay? You need to show first what f of A and what f of B are. So on your graph, what you have now is, hey, A, well, 0, and B equals 0.08. So let's calculate a sub 0 to kind of show the intermediate value theorem. You just got to show the endpoints. Calculate a sub 0, calculate a sub 0.08. All right, 0 should be easier to calculate. So we could do that one without a calculator. So a sub 0 means 1,000. In fact, common sense tells you at 0 time, how much money should you have? $1,000, right? Because you're starting. A sub 0, whenever you're doing that sub 0, that's always your initial value, right? And the math will show it to you because you've got 0 over 12 is 0 plus 1 is 1. What's 1 to the 60th power? 1 times 1,000 is 1,000. So what I need you doing, and you will need a calculator for this one, calculate 0.08 for me. And the squirrel problem was way more fun. This one's kind of like common sense, like, yeah, you know. Can I find a rate between 0 and 8% that'll get me to $1,400? Well, I'm going to try the 8%. What do I get? I need to know what 8% is. I can just plug. So you're just going to plug in 8%. What do you get when you plug in 8%? Well, in money, so let's round it 2 decimal places. What do you get? So again, proving theorems are funny things. Showing theorems work are funny things. Sometimes they seem rather, well, that makes sense, right? Because what you're showing here is you're saying, well, my initial investment is just $1,000. That's a sub 0. I'm going to guess I need at least 8%. So I'm going to try 8%, right? So I plug in 8% and I get $1,489. Well, maybe you can't find a bank with 8%. But you know if you can find a bank somewhere between 0 and 8% is going to be a magic percent that gives you exactly $1,400, right? So the only thing, the other way to do it is to keep just plugging in percents, right? You could keep, I'll try 0.075. Again, realistically, why wouldn't you just go with the 8%? Because at least you got your 1,400, right? So you can do that. But that is what you need to do to show. Now you can say, yes, by the intermediate value theorem, there must be a value R between 0 and 8% that will give me exactly 1,400. Okay? How to get that number? You can go to a graph real quick. Right? We have 1,000 parenthesis 1 plus, what was it? R. So I'm going to use X. Divided by 12 to the 60th. Woo. All right. And then you got to play with your graph. And you're going to go all the way, we're almost there, until you get to what? Hey, there we are. Woohoo! 1400. And then you're going to take your cursor and let me go down a little. Trying. I can't get to exactly 1400 apparently. So what's it about? 0.067, something like that. Everybody see that? So how would you tell exactly what it is? Just pop it on the graph and then you can do that. So you're going to play with decimals in one of these problems. Okay? Again, population growth, love those kind of problems. It's way more interesting to look at steady state. The interest, all you're doing when you get something on the lab that says show that there must exist a percent between these other 2%, you have to calculate the end, those 2%. And then you can state, by the intermediate value theorem, there must be a value between there. To get that actual value, you're going to go into Desmos to graph it. Okay? So that is the end of the lesson.